So now we're going to get into 2.3, and 2.3 is going to talk about derivative rules. So rule number 1, the derivative of a constant, the derivative of a constant, the derivative with respect to x of a constant is always equal to 0. So what does that mean? So if you have the derivative with respect to x of 2, that is going to equal 0. The derivative with respect to v of a constant is going to equal 0. So the derivative of a constant of a function is always equal to 0. And here, the derivative with respect to x of x is going to equal 1. So 2. And 3, we have the power rule. The power rule illustrates here, and look at what happens because the definition is going to change, but this is a positive integer. So the derivative with respect to x of a power term, x to the n, what that means is that the exponent now becomes the coefficient, and then you're going to reduce the exponent by 1. So what does that illustrate here? The derivative with respect to x of x to the third. Well, the exponent comes down, which is 3, and 3 minus 1 is going to illustrate 3x squared. So the exponent becomes the coefficient, and you reduce the exponent by 1. And again, this could be the derivative with respect to c, and this could be c to the 9th power. So therefore, you bring the exponent down, so you get 9, reduce the exponent by 1, and you get 9c to the 8th. Now what happens is if you have a constant in front of your power term. So that was the third rule. And let's get into, let me see if I could do this. No, there you go. So this here would be rule number 4. And the derivative with respect to x of a constant times a function. So pretty much you just are able to bring the constant out to the front and then take the derivative with respect to x of your function. So what this is going to illustrate is if we would write this as the derivative with respect to x, let's say we have a constant times x to the n, x to the n. So what this is going to illustrate is the constant gets multiplied by the exponent, and therefore you reduce the exponent by 1. I'm not going to get into the theory aspect because we're already, scratching time. This is going to come up in a discussion. But all of these definitions, they all have a proof. They all have a proof. And so if you take the derivative with respect to x, so dx, and let's say that this was 5x to the 4th, you can show a little work that you're going to take 5 times 4 times x to the 4 minus 1. Is that necessary? No, but sometimes these exponents are not going to always be pretty numbers, which are called the integers, and therefore you get the derivative 20x to the third power. And be careful of your notation. Rookie mistakes is not utilizing the proper notation. And I want you to notice that there's no dy here, right? Because the d all over the dx, that is the operator. That's telling you to take the derivative of this quantity. So what's going to happen is that our functions are going to have more terms. So what this is illustrating here, what number was that? 4. So now we're at 5. So now this is illustrating the derivative with respect to x of a sum of functions. And basically what that's illustrating, you take the derivative of the first term plus the derivative of the second term, provided that both of the functions are differentiable, meaning that that limit definition will exist. Okay, and then we have 6 is that the derivative with respect to x of f of x minus g of x is going to equal d all over dx times f of x minus d all over dx of g of x, not times. I meant to say of f of x, d over dx of g of x. So basically, we're just taking the derivative of each of those individualized terms at the same time using the power rule. So it's a little bit of work, but it beats using that limit definition. And just to give you a sneak peek, all of these definitions are how can I say, are utilize that limit definition. So I just pulled a couple of examples out of y'all's textbook. The derivative with respect to x here of a polynomial x to the 8th plus 12x to the 5th minus 4x to the 4th plus 10x to the 3rd minus 6x plus 5. That's a lot of terms. So a combination of the difference rule and the sum rule says that we physically can take the derivative of each of those terms. The derivative with respect to x of x to the 8th plus 12, which is the constant, times the derivative with respect to x of x to the 5th minus a constant, 4, of the derivative with respect to x of x to the 4th plus the constant 10 times the derivative with respect to x of x to the 3rd minus 6 times the derivative with respect to x of x plus the derivative with respect to x of 5. The derivative of a constant, 0. The derivative with respect to x of x is 1. And so for the remaining terms, the exponent now becomes the coefficient. You reduce the exponent 1. You're going to multiply the exponent and the constant, reduce the exponent to 1. Multiply the exponent and coefficient, reduce the exponent to 1. Multiply the coefficient and the exponent, reduce the exponent by 1. The derivative of x is 1 and the derivative of constant is 0. Again, it is not needed to write this particular step. And when you simplify all that good stuff, right, the derivative is going to be 8x to the 7th plus 60x to the 4th minus 16x to the 3rd plus 30x squared minus 6. And the original notation here, right, this, all of this is going to equal all of this. And in our intermediate steps, let's just write our equivalents. And you box the original, and then you box your final. Now, another example here I want to take a look at is example 4. And it gives you, find the points on the curve of this polynomial function where the tangent is horizontal. What does that mean? That the slope of the tangent must equal 0. So what this is going to illustrate first is we're going to have to find y prime, which is going to be a 4x to the third minus a 12x plus the derivative of 4 is 0. So typically I don't write that, but we will write y prime is going to equal 4x cubed minus a 12x. And now if we're interested in finding all the values, if we're interested in finding all points, well, remember that the points are x comma y. So when will y prime equal 0? So you're going to get 4x cubed minus a 12x equals 0. First rule is to factor out a GCF, and this looks like you're going to get x squared minus 3 equals 0. And so now when you set these factors equal to 0, you're going to get x to be 0, x to equal plus minus the square root of 3 when you use the square root property. Square root property, you get two solutions. The work comes into when you have to find the actual points. So you're going to have to replace x here, replace x here, and that's nice so that when you get 0. So we will illustrate here the points are, one is going to be 0, 4. Another point is what happens when you evaluate the square root of 3. So in this particular case, the square root of 3, that is 3 to the 1/2, so that's going to give you a 3 squared. So you're going to get y to be a 9. This is going to undo each other. Somehow I'm not, let me see. So if I put 3 to the 1/2, and I'm raising that to the 4th power here, and I'm getting 9. And when I put that in there, they cancel, and then I get 4. I don't know why this is not working. So when I look here, oh, because I read it wrong. Okay, so yeah, so you get 9 minus, what is that going to give me? 3, which is going to be 18 plus 4. So that is going to be a -5. And when you put the square root of 3 there, then you're also going to get a -5. So the points are where the tangent line is horizontal. And all of this would be my conclusion, and all of this would be my work.